Okay, hello everyone. Welcome, welcome. Happy Monday. Hope you all had a restful, relaxing weekend. Wanted to start off today just by kind of giving you some heads up about where we are in the schedule because things are kind of going to be a little bit different here in the next couple weeks or two. The reason I say that is because this is our third week of new material since the last exam. Normally we would have exam 2 after this week's worth of material. However, if you take a look at the calendar, you'll notice that's actually not the case. Exam 2 doesn't happen until November the 7th. So, ideally we would have the exam this week. However, if you look at Thursday of next week, you might notice that that's maybe not a super great day to have an evening exam. I know that I've got a little T-Rex and a little Kirby waiting for me at home that want to take a lap around the block and get a bunch of candy. So no exam next week. The exam is going to be the following week. So it'll be on November 7th. That is on the calendar. Just want to make sure you're aware of that. That is a little bit different than our usual flow. What does that mean for next week? For next week's material, we are going to keep moving forward. I can't afford to just drop a week, right? We have to actually keep moving forward. I am going to introduce Module 7 next week. However, that will not be on Exam 2. That will be on Exam 3. So I will remind you of this again next week as well. But what I'm covering in class next week, Module 7, is on Exam 3, not Exam 2. So Exam 2 covers everything up through today. This stuff will be on Exam 2. The stuff we're covering next week will not be until Exam 3 at the end of the semester. So I wanted to make sure that everybody was aware of that fact. The stuff on Canvas should be up to date. It should tell you exactly which modules are going to be on which exams, so there shouldn't be any surprises, hopefully. And just like we did for the prior exam, there will be a review session. You can see the week of the exam on November 7th. We're going to have a review session, and by the time we're here next week, all the review materials should be readily available for you. In fact, probably by the end of this week, all the exam review materials will be available for you on Canvas. So I just want to make sure you're aware of that little wrinkle in the schedule. Do with that information what you need to. If you need to not think about Module 7 before Exam 2, I honestly don't blame you, right? That's not an unreasonable thing to keep in mind. And the assignment for Module 7 is not due until after the exam either, right? So you do definitely have some extra time to get that assignment done. Again, not the ideal way to make the schedule, but just because of the holiday and other stuff, that's just kind of how it worked out. So I wanted to make sure you were aware of that. Otherwise, we're just kind of cruising along. Does anybody have any questions about schedule for the next few weeks or so before we hop into today's topic? Cool. Awesome. So today, we're going to be talking about kind of a rather infamous computer science topic. I've already had some students approach me and ask me about this topic. They know it's coming up. Maybe you've heard from students who've taken this course in prior semesters, or maybe you just know because you've done a little comp sci before and you ran into this topic and you're like, whoa, right? Like that's definitely a thing that can happen. Today we're going to be talking about something called recursion. So recursion can be a little bit imitating, can be a little bit conceptually difficult, but I'm going to show you a few examples today that hopefully will illustrate what recursion is and try and make it as simple as possible for you. And then, of course, like all the other concepts, you'll get lots of practice, hopefully, in studio this week and on the assignment as well. So actually, I can define recursion very simply. The definition of recursion is very simple. It's a method that calls itself. That's recursion. The definition of recursion in plain English is any method that calls itself. So this kind of takes us back to last week, right? We talked about methods last week. That was our big topic for Module 5. And that's a very common piece of advice that I'll give to students for this week as well. If this material is really tricky for you, it might be worthwhile to go back and review some of that Module 5 material. Make sure you're really, really, really solid on it, because we cannot talk about recursion without a good understanding of methods. But let's go back to that very basic definition of recursion, a method that calls itself. What is a method call? We talked about this last week. Somebody describe what a method call is? Something we discussed. Is your hand up?
When you call an already defined method, is there another method?
So yeah, so this is what we would call a method definition or a method declaration. This describes how a method works, but this doesn't actually do anything by itself. right? It's like if I look up a word in the dictionary, right? It'll tell me what the definition is, but it doesn't actually mean anything until I use that word in a sentence, right? The word by itself needs to be used along with other words to accomplish a task, for it to have an actual meaning. It's the same kind of idea with our methods. So this is defining a set of behaviors, but then I actually have to say, do this thing. And specifically, when I call the method, I'm responsible for plugging in values for this right here. I know this is another review question from last week, but good review for us before we hop into recursion today. What's that called? Starts with a P? Parameter. Yeah, good. That's a parameter. So when we call our methods, if it has any parameters, it doesn't have to, but if it does, we need to say what those values are. So this actually is a recursive method, and I can tell that very simply by seeing that the name of this method is factorial, and then down here I can see that I am calling this method factorial. That's recursion. That is quite literally the bare minimum that you need to have a recursive method. Now, that doesn't mean that we're just going to start slapping in recursive methods left and right all over the place. There are certain ways that we need to approach recursion, otherwise we're going to run into problems. And then there are also certain times when recursion is appropriate, and other times when maybe it's not so much. And I kind of want to start there by talking about what recursion is used for. Recursion is used to perform something that we actually have already been doing to a degree. Recursion is used to perform repetition. So what else do we use to perform repetition? Loops. Loops. Specifically, recursion and while loops have kind of a similar sort of feel to how they approach repetition, right? And so I would make the claim that many of the recursive things that you come across are going to behave very similar to while loops. In fact, we could even rewrite this using a while loop, and I think that's actually not a bad idea for us to do. We're familiar with loops, we're familiar with while loops, we're not so familiar with recursion, so having something that, uses a while loop to do the same thing might help give us some understanding about how recursion is working. So I'm going to make a new version of this method. I'm going to call it factorial loop. And this is a common thing you're going to see, at least in this class, right? I'm never going to use loops and recursion in the same method. Is the computer going to stop you from doing that? No, actually, it's not. Are there situations in real life in which you might want to use loops and recursion in the same method? Actually, yeah, it's possible. But I would say that, in most situations, including many of the situations we see in this class, it's going to be a one or the other type situation. In fact, for some problems, I'll specifically tell you, you got to use recursion for this one. You can't use loops. Or maybe even the opposite. You shouldn't use recursion for this one. Please use loops, right? They are two tools that accomplish the same thing, so we don't often see them used at the same time together. They're off. It's going to be a one or the other kind of situation. But otherwise, I'm going to keep this method exactly the same. And using the code up here, we can kind of visualize how this method is going to work. If we make up a number for n like 4 that we see down here, try this out in a little bit. We first check to see if that's 0. Well, 4 is not 0. Otherwise, we return 4 multiplied by the factorial of n minus 1, which is 3, right? Factorial of 3. And so how can we accomplish the same thing with the loop? Well, we'll need a variable to store our factorial, right? Maybe I won't call it factorial. Maybe I'll call it result instead. We'll set this result equal to not 0, actually, but maybe 1 would be a better choice, especially since we're doing multiplication. And multiplication by 0, right, leads us in a very, not the direction we need to go in. So I'll set this to be 1, and then while n, we could even say while n is not equal to 0, which is exactly the opposite of what we're saying here, right? While n is not equal to 0, we need to keep repeating. We'll say the result is equal to the result times n, and then we're just going to subtract 1 from that. finally, at the very bottom, we can just return our results. And I'll run through both of these in the debugger and run them for you in a second just to show you exactly how they're working. But let's compare and contrast kind of what we see, right? We see this while loop with the condition. This condition here, while not exactly the same, is very similar, right? It's determining when we stop. It's determining when we stop. Notice that if n is equal to 0, we don't actually have that recursive method call here anymore, right? It just says return 1. This is our stopping point. This is the end point for our recursive method. We have a name for this. This is called the base case. This is the base case. Otherwise, if we haven't hit our stopping point yet, that means we have work to do. So what do we need to do? We need to multiply by n, and then we're going to subtract 1 from n, and then we're going to keep repeating until n is equal to 0, at which point we stop. And that's what's represented in this code down here. You can see that while it doesn't look exactly the same, right? You can see the multiplication by n that's happening, the subtraction of 1 that's happening with n every time through the loop. The way to think about this, one trip through this while loop is equivalent to one trip through my recursive method. The whole thing, start to finish. So one pass through my recursive method is roughly equivalent to one iteration through a while loop or a for loop, depending on how you get there. But let's run this through the debugger, especially the recursive one. I'm not so worried about you understanding how the loop one works. Loops we've covered in pretty significant detail. But I want to run through the recursive one in the debugger, definitely, and show you how this is going to work. So I've set my breakpoint here on line 27. We're going to be computing the factorial of 4, and maybe I should have started with this, but if you need a little reminder of factorial, if it's been a little while, that's just going to be 4 times 3 times 2 times 1, right? Equals 4 factorial. So this number grows pretty big, pretty fast with the multiplication. But we should get 2, 6, 24, right? As our answer. First, let's just run it straight up and make sure that we actually get that. There's our 24. But how? How do we get that? What's the actual flow? What's the actual execution like? Well, let's start this in the debug mode. And take a trip through our recursive method. I'm going to click the step into button here so that we hop into our recursive factorial. Notice that we started with the value of n is equal to 4. If I look over here at the method call stack, this is very important, especially when dealing with recursive methods and understanding how they execute, right? You'll see that I started in main, and then factorial is the method that I'm in now, right? So I see a value of n is equal to 4. The first thing that we're going to do, in the vast majority of recursive methods, is check the base case. Are we done yet? Should we stop? That's the first thing we're going to do. Here we're saying that if n is equal to 0, that's our stopping point. We're gonna end. But we're not 0 yet. We're 4. So we're gonna jump down to this statement, and so it says, all right, I want you to do 4 times the factorial of n minus 1, which would be 3. Well, I can't compute what this is until I figure out what this is, right? I don't know what this entire statement is going to be until I figure out what this little piece of the statement is. This is the recursion. This is what we would call the recursive step. I would probably even mark it as such. This is our recursive step. So because this is a method call, I can actually use step into and pay attention to where we are now. I'm back at the very beginning of the method. This time n is equal to 3. And notice over here on our call stack that I see main, and then I see 2 calls to factorial, right? This is our second trip. This is our second pass. This is our second repetition through the recursive method. So however many times we need to repeat until we get to the base case, that's how many times I'm eventually going to expect to see this pop up over here. But this process is just going to keep running over and over again. So we're going to say, all right, 3 is still not 0. So I need to do 3 times the factorial of 2. So we'll step into that and we'll see, okay, n is now 2. Pay attention, there's 1, 2, 3 versions of the factorial method. These are all independent of each other, right? These 3 versions are all existing independently. They're all waiting. They're all waiting for us to eventually get to a point where we can start figuring out what the answer is. But we're not there yet. N is still equal to 2, which is not 0, so we keep going. N is now equal to 1. Our stack grew even bigger. Still not to our base case yet. But if I go one more time, all right, here we are. N is equal to 0. The factorial of 0 is just defined mathematically as 1, right? So if I step this time, you'll see, all right, we've made it. We've hit our base case. We've hit the base case. But think about what needs to happen. We're not done yet. All of these methods are still sitting here waiting to get the result. This method is waiting to get the result from here. This method is waiting to get the result from here, and so on and so forth. So now that I have this answer, I know what this is. This is 1. Factorial of 0 is 1. I'm going to take that 1, and I'm going to return it. That means I'm literally passing that value of 1 out of the method to where it was called. So the next time I step, we'll see that factorial returned 1. I'm now in the version of factorial where n is equal to 1, right? So it's now saying 1 times 1, which is actually still 1, so not terribly exciting from a multiplication perspective. But every time I click step after this, we're actually working our way back up the stack towards where we originally started from with the value of n is equal to 4. And the multiplication is being performed on the way back up from the base case. So next time you'll see, all right, the stack shrank. One method was over. So now I'm in the version where n is equal to 2. So this is saying 2 times 1. Now I'm in the version where n is equal to 3. So this is saying 3 times 2. That should give me a value of 6. Now I'm in the original version, the one that I called, with a value of 4, right? So now it's saying 4 times 6, which should be our final value of 24. And in fact, that's what gets printed out down at the bottom. That is how the vast majority of recursive methods are going to be structured and how they're going to work. You can have recursion without a base case, right? But it's not going to end very well for you. We need to have a base case, which is where we stop, and we need to have a recursive step, which is telling us to keep repeating. There's more work to be done. There's more repetitions to do. Are there any questions about those two pieces? Got more to talk about, but just want to make sure we're all on the same page so far. I think it's important to understand that, so how do I choose the base case? How do I choose what that recursive step is? Those are tricky parts, tricky things to consider. For this problem, the base case kind of was, we're looking for a natural ending point. So if I'm talking about factorial of something, I clearly see that descending pattern. I clearly see that I'm eventually going to get to 0, right? So 0 is kind of a natural stopping point. Can't really take the factorial of negative numbers. I'm not really sure what that would... Maybe there is a mathematical definition for that. I'm honestly not sure, to be perfectly frank with you. But in this case, once we hit 0, we're done with the factorial, right? How do we do the recursive step? It's actually important that the recursive step does not just do any recursion, but does recursion that is taking us closer to the base case. Does that make sense? So notice how I'm assuming that n is some positive value, and every repetition it's going down by 1. So I know that it will, for a fact, eventually be 0. If that's not the case, right? Here's a couple of different ways in which we can mess up recursion. Let's say that it doesn't trend towards the base case. What's going to happen here? I plug in a value of 4. It says, is it 0 yet? No. So multiply it and then take the factorial of 4. And then it says, oh, is it 0 yet? No. Multiply it by 4 and then take the factorial of 4. Can you kind of see what's going to happen when I do this? I error it out. If I was comparing this to my while loop example, this is equivalent to me doing this, right? Taking out the n minus minus. So for the while loop, what does that lead to? That leads to infinite while loop. And recursion, it actually also leads to infinite recursion. However, the computer won't let you do infinite recursion. You're eventually going to run into this stack overflow error. It's a very classic error that you see when doing recursion. What does this mean? This means that we're doing recursion. I have a method that's calling itself. At some point, the computer's like, we've been recursioning for a while now. I don't think this is going to stop. So I'm just going to stop it and be like, hey, you've gone too far. I think the limit is by default set to be like 200 or something like that. So if I'm doing 200 repetitions in my recursive method and I still haven't hit the base case, the computer's just like, well, I think this might be infinite. I'm cutting you off, right? Check your base case. Check your recursive step. Make sure that you actually are stopping at some points. So yeah, if you see a stack overflow error, that's very similar to writing an infinite while loop, just using recursion instead. Or the other thing, of course, is, what if I just don't have a base case at all? Kind of a similar story, right? If I just forget to put one in, this is still technically recursive. Again, for a method to be recursive, the only thing that it needs to do is call itself, right? That's the only thing that needs to happen. But this is obviously not going to stop either. N is going to keep going down, keep going down, keep going down. But it never says, hey, if n is less than some value, you need to stop going down, right? It's just going to keep going down forever and ever and ever and ever and ever. This is like writing a loop that has a bad condition, right? Saying, well, if I said, well, n is greater than 0 here, or how would I say a bad condition for this one? Well, n is less than infinity or something like that, right? It's like having a bad while loop condition. So both are things that we're, used to being conscious of with our while loops. It's the same kind of idea with our recursive steps. If you run this, you'll get the same exact stack overflow problem. It says, you're doing recursion, but you're never stopping. You're never going to end. So a lot of times students understand these concepts. But then what I'm going to do in class, or maybe on the exam that's coming up in a couple weeks, is I'm going to give you a problem. I'm going to say, turn this into recursion. And that's hard. That's tricky, right? It's one thing if I give you some recursive code, a lot of people can kind of dissect it, get used to how it works, the execution. But it's tricky to come up with this stuff. So let me try and help you out with that. The way that we come up with these recursive ideas is to identify something called the recursive substructure of the problem. And so what that means when I say recursive substructure is I'm trying to define the problem in terms of itself. I'm trying to define factorial in terms of factorial. I'm trying to use the definition of factorial to define what factorial is, which I know is kind of conceptually mind-bending, right? But let me show you what I mean by using this factorial example. The recursive substructure, if I wanted to, I could say 4 factorial is equal to 4 times 3 factorial, right? That is a thing that I could say that is, in fact, accurate. And you can see that I've defined 4 factorial in terms of 3 factorial. What we really want isn't a specific example, but we want one that's more generalized. So how can I define n factorial for any given positive value of n? Well, that would be equal to n times n minus 1 factorial. If I try to generalize that out, this is what I would call the recursive substructure for factorial. And it, hopefully you noticed, right, that this little part right here shows up in our solution. N times the factorial of n minus 1. There it is right there. If you've identified the recursive substructure of a problem, then what you've really identified is the recursive step. Turn that into code, figure out what your base case is, and then you've got your recursive method. I know I'm making it sound easy. It's not that easy. It's definitely tricky. Definitely hard to wrap your brain around things. Let's do something else that'll kind of help us understand recursive problems even more, and also is a thing that I very commonly ask people to do on the exam. I want you to get better and better at evaluating how these recursive methods work. And one way that you can show me that you understand how recursive methods work is by doing something called the substitution method. So I'm going to go through an example of the substitution method with you right now. It helps if I spell it right. Substitution method. There we go. So typically on an exam or other problem that I give to you, I'll say, show the substitution method for, factorial of 4. And what I'm asking you to do is quite literally tell me step by step how this is going to execute. When I ask you to perform the substitution method, what I'm really asking you to do is pretend that you're the debugger, really, and walk me through this recursive execution step by step by step. So how would I do that? I'd say, okay, factorial of 4. I plug in 4 for the value of n. I'm doing this all in my mind on paper and pencil, right? Just like I would expect you to do in the exam. All right, n is 4. I haven't hit the base case yet, so that means that I need to do 4 times the factorial of 3. And so I would actually write that down here as part of my substitution method. It's equal to 4 times the factorial of 3. Okay, but now I have to figure out what the factorial of 3 is. I don't know what the factorial of 3 is, so that continues my substitution method. I'll say the factorial of 3 is equal to, well, we still haven't hit the base case, so it's going to be 3 times the factorial of 2. All right, well, now we have to figure out what the factorial of 2 is, because I don't know what that is yet. So I would say the factorial of 2 is equal to 2 times the factorial of 1. Kind of see the pattern that's coming up through here, right? Factorial of 1 is equal to 1 times the factorial of 0. And now we get to, kind of an exciting part. Since 0 will trigger our base case, no more recursive steps. The factorial of 0 is just defined as a constant, 1. We're not done with our substitution method yet, though, because remember, the answer to this is 24. So I'm hoping that by the time I'm done, I get that answer of 24 back out. In fact, we haven't done any substitution yet at all, but we're about to. This next part is where the substitution method gets its name from. Now that I've hit the base case, and I know what this value is, I can substitute this value, this known value, in on the prior step. And so we're going to work our way all the way back up doing just that, substituting those values in. So I'm going to revisit the factorial of 1 and say that's equal to 1 times 1, because I've substituted this 1 in for the factorial of 0. I've made that substitution. So we know that this is equal to 1. And now that I know what the factorial of 1 is, I can revisit the factorial of 2 and substitute in this value for the factorial of 1. We're going to do that all the way back up to the top, right? Factorial of 2 is equal to 2 times 1, which is equal to 2. And now that I know what the factorial of 2 is, we'll substitute that in to this expression here. Okay, so it's going to be 3 times 2, which is equal to 6. And then finally, the factorial of 4 is equal to 4 times 6, which is equal to 24. There's our 24. That's our answer for factorial. Are there any questions about this process? It really involves going all the way down to the base case, but then you have to go all the way back up to where you originally started from as well. Don't get all the way down to the base case and then just think that you're done. 1 isn't my answer, right? 1 is part of my answer after it gets multiplied in with all that other stuff. You have to work your way back up, perform those substitutions to get the proper answer back out. But again, I want you to notice that this is exactly the same path that I took through this method in the debugger. Quite literally the exact same trick through this code as I did in the debugger for you a few moments ago. I would very much encourage you to do that debugging on your own as well. Make sure you understand that flow through this recursive method. We're going to take a look at least a couple more examples here today. Does anybody have any questions about this example before I move us on to another one? All right, cool. Let's take a look at another example. This one is one that I made up before class today. It's actually not in the materials that I provided to you, but that's okay. It's still a good, interesting problem for us to talk about. And I provided us the loop version of a method that I'm calling countOdd, right? And so it takes in, we're using arrays. So hopefully we're comfortable enough with arrays to be talking about them. Yeah, and the idea behind this method is that I'm going to count how many odd values appear. So if I pass in this array right here, I would expect to get 3 back out because 1, 3, and 5 are odd, and then 2 and 4 are not odd, right? So I want to get the number of odd values that exist in this array. I can show you that this non-recursive version works. Obviously, we're interested in creating a recursive version. Let's make sure this actually works properly. Yes, it does. Let's try this approach a little bit differently. I want to, kind of sketch some things out on paper because in the real world, in the real practice, I don't necessarily have this nice code to work off of, right? I have to sit down and figure out this problem myself. So how would I actually figure this out? Let's try and work through an example and see if we can't identify what the recursive substructure might look like. I'm going to say, all right, countOdd of 1, 2, 3, 4, 5 is equal to, how can I define this as, in terms of itself? Well, think about how the loop's doing it. Every time through the loop, I'm checking how many values from my array. Take one trip through the loop, and I'm checking one value from my array every trip through the loop. We want our recursive method to do the same thing. So if I say, I want you to tell me how many odds are in this array, I want my recursive method to approach this the same way. I want it to look at this first value and say, are you odd or not? Yes or no? And if the answer is yes, then I know that I have, at least one odd value, but I still have more work to do. I also have to see how many odd values are left in the rest of the array, right? And that's actually kind of where the recursive substructure is going to come in. It's like, it's going to say, yes, there's one odd value plus countOdd of 2, 3, 4, 5. Right? The first value is odd. That's what this is representing. The fact that I have one odd value plus however many odd values are in the rest of the array. Does that make sense? For a recursive substructure? Now, I think this is a good recursive substructure. The problem is that unlike the last problem that we saw, taking this recursive substructure and converting it into something that is in fact actually recursive is going to be a little bit trickier. And the main reason for that is going to be because we have this array here. Does anybody see a problem with this line of code and how, at least as it refers to arrays? What's the issue? Look at the array I start with, and then the array that I say I want to use for the next step. It's shrank, right? But we don't really like shrinking arrays too much. That's not an easy thing for us to be able to do. So that's kind of tricky. Notice the for loop doesn't shrink the array. It uses that I value to track where it is in the array. Can we do something like that here? Could I have an I value or some other value that I'm using to track where my position is in the array? Just like the loop does? Yes, we can. We can do that, but we have to be a little bit careful about how we approach that. Let's start to piece together a recursive version of this method now. We'll call it countOdd recursive. I'm going to start by taking in the array. This is the array that I wish to count the odd values of, right? And we're saying that I need to have, some representation of I. It's going to help me out to have some representation of I. So int I is equal to 0, let's say, right? But then, I'm kind of struggling with where to go next, because every time I call this, it's going to set I to be 0. And that's not necessarily what I want. I want I to go up. I want I to go up, 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 up. Or think about it this way. When I go through this method the first time, I want I to be 0. The next time I go through, I want it to be 1. The next time I go through, I want it to be 2. If I say I equals 0 right up at the top, that's hard for me to do. That's difficult for me to do, right? I think the issues that we're kind of running into are that since every value that we're checking is a different trip through the method, methods can't see variables from other methods. What's that called? Scope. Methods cannot see variables that exist in other methods. So if I set I equal to 7 here, the next time I call this method, it's not going to know that that value of I is 7. It's going to have its own unique copy of I that's going to be set to 0, right? So how do I fix that? How do methods communicate with each other? How do I get information into and out of methods? Yeah. Parameters. So oftentimes when using recursion, we're going to have a need to introduce additional parameters to our methods in order to make the recursion happen. This is a classic example of when we would want to do that. The problem is that I don't want to do that here. I don't want to add an int I here. Think about what this means. If I add the parameter here, think about what this means to someone that wants to use this method in the future. They're going to say, I want to count the odd values that exist in my array. They're going to try to call your method. They're going to plug in the array, and they're going to be like, all right, go. And then this code's going to be like, that's not good enough. I also need this value I. And then this person's going to be like, what do you need a value I for? I just want you to count all the odd values that are in my array. I don't care what I is. I don't know what I is for, right? I just want you to count the odd values in my array. I don't care how you do it. Just do it. Leave I out of it and tell me how many odd values are in my array, right? So this parameter is not for the outside world to worry about. It's what I would call an implementation detail, right? This is something that we need as programmers to get our recursion working, but the people who are using this code don't care about. So, how do we fix this issue? Well, we're going to introduce another method. This is a very, very, very common thing to do with recursion. We're not limited in the number of methods that we have. We can create as many methods as we need to do whatever functionality we need our methods to do. So I'm going to make a method down here, and this method, they're so common, we have a term called helper. These are helper methods. Helper methods. Helper methods are often used with recursion to do two different things, one of which I've already shown you. If I've determined that I need additional parameters, right, then I can use a helper method to provide that. Think about what this method is going to do. It just needs to call the helper method to kick things off. And it needs to provide an initial value for I. So what does this become? This becomes count odd helper. We'll pass the array through, and we'll just plug in 0 for I, saying, let's start at the first position. The helper method, this is the one that's going to be recursive. The non-helper method up here, no recursion, usually just kicks off the helper method. Another reason why you might want to consider including a helper method. So the one reason that I illustrated was I need additional information. I need an additional parameter to make my recursion happen. Another reason why you might want to do it, if there's anything that doesn't get repeated, So if there's any piece of code that just needs to happen once, that's going to go in the non-helper method. And then anything that's getting repeated is going to go into the helper method. In fact, you can see that I kind of did this part here, right? I can make that even more explicit if I wanted to by saying, int count equals 0, and then just plug. Actually, it's not count. That's I. Whoops. It would be I is equal to 0, and then plugging in I. So I'm kind of doing this part in my non-helper method, but then everything that's inside of the loop, that's what's going to be done recursively. So let's talk about that. What's my base case? When do I stop? If I'm following this level of substitution, I'm going to keep going, keep going, keep going, keep going until what happens? Yeah.
You get to the last value in the array.
I'm at the end of the array. I'm at the very end of the array. Once I get to the 5, I just have to check the 5 and then I'm done. There's no keep going after that, right? Or in other words, it's based on the length of the array. When the number that I'm currently looking at, which we have this parameter I for that purpose, or I could say this a little bit differently. I could say if I is greater than or equal to the length of the array. So if I is off the end of the array, how many odd values am I going to see? Zero. If I is over here, if I is off the end of my array, I see 0 odd values because there are no values for me to look at. I'm going to trust that my other trips through recursion will pick up these odd values. I'm checking one at a time, right? I'm checking one value at a time at position I. So if my position I says I'm off the edge of the array, is that value odd? No, it's nothing. There is no value. Yes, question? This is my base case, yes. This is absolutely my base case. The base case, to kind of review, is it's the ending point of our recursive steps, but it's also a known value. It has to be a known value. We could have done this backwards. I could have started I at the back of the array and worked my way forwards. That's also how we could have approached this, right? That's just not how we chose to do it. But if I've gone off the end of the array, how many odd values do I see? 0. Or think about if the array was empty. Think about if I tried to fool you, right, and just gave you an array with nothing in it, right? How many odd values are in an array with nothing in it? 0. 0 odd values. Otherwise, this is where our recursive step is going to be. But we have to check the odd versus even first, right? We have to check the odd versus even first. So first I need to do this stuff. If the array, such and such, I'll just copy that. If this is checking the odd value, if I make it inside of this if statement, I've seen one odd value, but I still have to check the rest. So if we look at our substitution down here, we'll see that it says 1 plus count odd of all of the rest of the values. Well, we're going to say that a little bit differently because we're not shrinking our array. We talked about how that's a tricky thing to be able to do. We're going to use I instead. So I'll say count odd, and then the value for I is going to go up 1. So if I is 0 the first time through, the next time through the array, I'll look at 2. And then the next time through the array, I'll look at 3, and so on and so forth. And this is our answer. What if the value is not odd? What if it's even? Yeah. Oh, it should be helper. Thank you. Should be the helper. Yeah, great catch. The helper method is the one that is recursive. So the helper method is the one that should be calling itself. If you are using a helper method. Not all of them need helper methods. So the first step is, do I need a helper method? If you do need a helper method, then the recursive stuff goes in the helper method. The non-recursive stuff goes in the non-helper method. All right. The question was, what happens if it's not odd? What do I do? Let's think about it. I could write this out. Count odd of 2, 3, 4, 5 is equal to, how many odd values do I see here? 0 plus count odd of everything that comes after it, which would be 3, 4, 5. So I actually need to have a recursive step in 2 places. I don't need to say the 0 plus, that's a little redundant. I can just say count odd helper array I plus 1. So if it's odd, then I have a 1 to represent that I see that odd value. If it's not odd, then I just move on to the next value. I don't add anything, I just move on to the very next value. I think we're done, but I want to prove it to you, right? I want to walk through this in the debugger and see exactly how this code works. Make sure you understand how this code works. We've covered a lot of new ground here. We actually have a problem with our method up here. Does anybody see what the issue is with this method? I don't return anything. The return type is specified as int, but the word return never shows up. If you have anything besides void here, the word return has to show up somewhere inside of this method. It should go right here. Now, what I'm going to do is I'm going to switch this to be our recursive method. I'm going to set my breakpoint on that method call, and let's walk through this and make sure we understand exactly how this is working with the helper method and all. So I'll start this up in debug mode. And here I am on line number 7. Notice that we're in the main method, so we haven't actually gone into any other methods yet. We're still in main. I hop into my non-helper method. You can see that all it does is it sets the initial value for I and then kicks us into our recursive helper method. So this is never going to be doing the recursive stuff. It's always going to be kicking us into the helper method if we have one. Once we go into the helper method, we're going to start looking at our base case and check to see if we still have more work to do or not. So if I is less than the length, well, it's not. Or I'm sorry, if I is greater than, it's not. So we're going to keep going. If the value is odd, then I need to do 1 plus and then move on to the next step. So I'm going to jump in and notice that now I is 1. And I'm going to be examining the value at position 1, which in my array we can see is even. So this time through the loop, still haven't hit the base case. It's not odd, so this time I'm going to do this recursive step down here. All right, I'll step into that. Still going through, I'm now at I is equal to 2. That is an odd value, that's 3. Notice my stack over here is growing. Notice too that I can actually click on any of these and it'll tell me, right, that the very first one I was 0 and the next one I is 1 and the next one I is 2. It'll actually show me all the variables for each one of these different versions of the method that exist. But we're going to keep going. We're going to keep going until we hit our base case. So we're still not there yet. The value of position 3 is not odd. I think we have one more trip before we hit our base case. All right, so now I is 5. That is equal to the length. That means we've hit the end of our array. We have to go all the way back up to compute our answer. And notice that it's actually doing the counting on the way back up, right? I've got all these 1 pluses that are sitting there waiting. And on the way back up, that's when they're actually going to get summed up. So here I'm going to return 0. I'm going to take that 0 and I'm going to substitute it into this version of the method call right here. It's going to return 1 plus 0. Okay, that's 1. Well, this one is not going to add 1 to it because that was an even number that we detected. So the answer is still going to be 1. Okay, here's another odd value, so we're going to add 1 to indicate that odd value. But then the next one was even, so we don't add anything this time, right? one more odd value. I believe that's the very first one. So this is our last trip. And then we can see that here's our 3. Here's our number 3 that we're going to pass all the way back up to the main method and then print out. So that recursive version of the code, I'm making the claim, I tried to illustrate, prove it to you, I'm making the claim that this version that uses the for loop is computing the odds in very much the same way as this recursive method, right? The main difference being that we're using the recursion to perform the repetition for us, not the for loop. Are there any questions about this approach? I know this is trickier than the last one. I have one more example that I want to go through with you today. I also want to say something else about this example before I move on. I like this example because it's a good illustration of when to use helper methods. You're going to get practice using helper methods on the studio, and you're also going to need to use helper method on probably at least one of the homework assignment problems this week. But let me say this. If somebody came to me and said, hey, write a method that counts how many odd values exist in an array, how do you think I'm going to do it? You think I'm going to do it this way, or you think I'm going to do it this way? I'm doing it this way. I'm doing it this way. 99 times out of 100, right? Am I going to understand that I could do it recursively? Sure. Anything that I do in a for loop or a while loop, I can also probably do recursively. That doesn't mean it's a good idea to do it. That doesn't mean that it's, the best way or the easiest to understand way. If you understand how to get to the solution better with a loop, then you should use a loop, right? That is a fact. And so then the next question is, well, why the heck are you showing us all this stuff then, right? Like, why are we taking all the time to do this if you're telling us that it's okay to use loops? There are some problems. There are some problems that just naturally lend themselves to using recursion. So the last problem that I have for you today is one such example. These kinds of problems, while they can be done recursively, in my opinion, maybe not the best way to do it, right? Good way to learn, good way to see a different approach to a problem. But the one I'm going to show you next falls into a category of problems called divide and conquer problems. And you'll see these problems pop up again if you take any further computer science classes after this one. You'll see these problems come up in 247 and in 347. It's a very common, grouping of problems that we like to solve. The idea is that I can break the problem up into smaller versions of that problem and then divide and conquer, as in here's a problem that I can break up into 4 versions of this 4 smaller versions, and then send one person off in each of those 4 directions, right, to work on the smaller copies of the problem. So a lot of these divide and conquer problems are visual in nature. They don't have to be, but a lot of them are going to involve drawing things on the screen. And that's the one I'm going to show you. It's going to involve drawing stuff on the screen. We're going to make graph paper. And let me run this program for you real quick and show you what it does. Actually, it doesn't do anything yet because we haven't finished writing the code just yet. But what do I want it to do? I want it to make graph paper. And by graph paper, I mean I want it to draw a grid. That's literally it. I want it to draw a grid. I want to draw a grid on the screen, but I'm going to do it recursively. I want to do it recursively. This is an example of a divide and conquer problem. Consider that I can draw a grid across this entire screen by sectioning it into 4 quadrants, right? And then drawing a grid into each of those 4 quadrants. So each of the 4 quadrants that I define is a smaller version of the big problem I'm trying to solve, which is drawing a grid. But then actually you can take each of those small sections and break those into 4 sections, right? 4 grids, and do all of those. So it's a classic example of divide and conquer. So let's start to piece this together. We've already got you set up with the method call. And then also, this is our base case. We're saying that, all right, when the size gets small enough, I'm not going to be able to see it anyway, right? It's too small for the human eye to even determine, so we're going to stop. If the size of the grids that I'm drawing is too small, actually this number right here determines how big the grids are going to be, right? if I want giant graph paper or very fine graph paper, this is the number I would change right here. The size, this is telling us the length and the height of the current square that I'm trying to cut into quadrants. And then these two values represent the x and y coordinates of the lower left-hand corner of the square that I'm currently trying to divide into 4 quadrants. So our first step is to actually draw those lines that are going to divide it into quadrants. That's actually pretty straightforward, although I might pull up the API here real quick. This is a good review of how to find things with the standard draw API. There's got to be something in here called line, right? Here we go, standard draw.line. How does it work? It wants to take in x0, y0, x1, y1. Well, that's pretty straightforward, right? X coordinates, y coordinates. So I want to do standard draw.line. The square that I'm starting with, the lower left-hand corner is 0, 0, so that's here. And then the size is 1, so the entire screen, right? I want to draw a line that sections it in half horizontally, and then one that sections it in half vertically. So how do I draw those two lines with that information? Well, it's going to be the lower left x plus half of the size, right? To get me that x coordinate. Let's draw the vertical line first. So it's going to be based on the lower left x plus size over 2. That's my x coordinate. My y coordinate will just be lower left y, correct? And then the x coordinate doesn't change. It's a vertical line, so it'll be lower left x plus size over 2. And then the y coordinate at the top would be lower left y plus size. Does everybody understand where I got these numbers from? I'm trying to draw a vertical line based on the coordinates for lower left x and y and the size. So I said, all right, halfway across would be size over 2. Add that onto the lower left x, and that gets me this x position. It's the same at the top and the bottom. The y coordinates are going to be whatever the lower left y coordinate is, and then lower left y plus the size gets me the top. I can actually run this again. Should hopefully see a vertical line this time. Oops, I made a mistake. What did I do? Oh, I forget a semicolon. Wow, that's like one of the easiest mistakes to make. All right, let's try that again. Hopefully I got my vertical line this time. There it is. Yeah. Now I need to do a horizontal line. It's going to be a similar process. The x value for the horizontal line will be lower left x to start with. The y value needs to go up by size over 2. The x value on the right-hand side will be lower left x plus the size. And then the y value won't change. It'll actually be the same. Semicolon. Don't forget the semicolon this time. And now hopefully I have a cross. All right, cool. Beautiful. We haven't done any recursion yet, but we're about to. Think about how this recursion can work. I have a way of drawing a cross in the middle of a square. I'm going to say, go to that top left square and draw a cross. And then I'll say, go to the bottom left square and draw that cross. Go to the bottom right square. But I'm going to use recursion to do that. I'm going to use recursion to do that. So if I want to say, go to the top left square, what information do I need to provide? I need to provide the x, y coordinates for the lower left corner. I should be able to compute those, as well as the size, as well as the distance across. Let's try that. Let's try that using our recursive call. The name of the method is GP for graph paper. Let me mark this as I'm going to do the upper left quadrant first. Okay? So if I start with the big square, the entire screen, and I want to go to the upper left quadrant, my x value stays the same, correct? My lower left x value stays the same. My y value goes up by size over 2. And then what happens to the size itself? It gets divided in half, right? It used to go all the way across the screen, but now it just needs to go halfway across the screen. And with this recursive call, let's take a look and see what happens. Okay. Just as I was hoping, it drew across in this first one, but then it didn't stop. It actually drew across in the upper left quadrant here, and then the upper left quadrant here, and it kept going. It kept going to the upper left quadrant until the size got to be less than 0.5, right? Well, now we just need to do the same thing for the lower left quadrant and the upper right and the lower right quadrants. This is where the divide and conquer gets its name from. I'm not going to do recursion once. I'm going to do recursion 4 times, once for each of the 4 directions that I want to go. So divide and conquer problems like this are going to have multiple recursive calls, one for each of the divisions that are being conquered. So if we want to write one for the lower left quadrant, we just need to tweak these parameters a bit. Let's see, the x value is still not going to change, right? The y value is actually not going to change either. The lower left and lower left, yeah, those are going to be exactly the same as they are for our current step, and the size is going to be divided by 2. This should point out the lower left quadrant, and if we run it again, we'll see that it still does the upper left first, but then, oh, it also comes back and picks up the lower left quadrants, and eventually it will do this one down here. Kind of mesmerizing. All right. Let's keep going. We've got 2 more. We'll do upper right quadrant. So for the upper right quadrant, starting from this point, I need to get to this point. They're both going to be shifted up by size over 2, right? Since this is the lower left-hand corner of my quadrant, so both of them need to be shifted up by size over 2. Do a little copy pasting to make that happen. Whoops. Got a little overzealous with my copy pasting. There we go. Parentheses, semicolon. Yeah, all right, cool. So that should take care of, I'm gonna speed this up a little bit. This is pausing half a second. It's gonna start taking too long, so I'm gonna speed it up a little bit. There it goes. Now it's doing the upper right quadrant as well. And you can see that the only step that's missing in any of these is the lower right quadrant that we haven't written yet. Let's go ahead and do that to kind of finish out this problem. And so that would involve shifting the x coordinate, but not the y coordinate, by size over 2. And I think that should give us the full screen covered in our grid. I like doing this step by step with you because it helps show, A, how divide and conquer programs work, but you can see that the recursions, what's interesting but also kind of mind-bending, right, is that all of those quadrants are being split into quadrants, and then those quadrants are being split, and it just keeps going all the way down until it's covered the entire screen. I want to illustrate too, or I want to kind of actually double back for a second and talk about this base case a little bit more, right? This base case is a little bit different than the ones that we've seen before, since it's based on the size, and it's also kind of arbitrary. So if I stick another 0 in here, I'm going to get a lot more detail in my graph. Oh my gosh, it's drawing tiny squares, maybe a little bit overboard, right? Maybe 0.01 would be a little more acceptable. I don't know. Okay, yeah, not as tiny for that one. So yeah, we can adjust our base case to illustrate how deep, how fine we want our graph paper to be. So this is kind of a nice little tweak. Does anybody have any questions about this problem? I know this is different than, I mean, all three of the problems we've looked at today have been kind of different from each other, but they all involve recursion. They all involve repetition. Could you think about how you would do this using loops? Think about how you would write this program using loops. Probably be pretty different, right? You would probably do it, you know, going across, drawing all the vertical lines, and then going down, drawing all the horizontal lines. At least that's how I would approach it if I were going to use loops to do it. Again, is that an acceptable thing to do? Yes, absolutely it is. But there are some problems that you are going to run into where this divide and conquer approach is just going to be a very natural fit. And using loops, while maybe technically possible, is going to be considered the more complicated solution than just using recursion. There is a data structure that we're not actually going to talk about in this class, but in 247 you'll talk about it. The data structure is called trees. Trees and recursion go together like peas and carrots. They are just you know, good friends, right? Anytime you're working with trees, the chances of you using recursion to help you process those trees is quite high. They just go that well together. So, well, a lot of the examples that I went through today, and honestly, a lot of the stuff that I'm asking you to do in Studio and the stuff that I'm asking you to do in the assignment, that could all be done using loops. And in any other context, I'd be like, yeah, sure, use loops. We're trying to get you ready for recursion so that when you do see trees and you do see situations, divide and conquer problems where using recursion is appropriate, you've got some background in it. It's not your first time thinking about this idea of recursion. We're trying to get you to practice this skill, get a little bit used to this idea of recursion, so that if and when you take up our level comp sci, you've got this tool in your pocket. All right. Does anybody have any questions for me? Anybody want me to go back through anything? If not, that was all I had on my agenda for today, so I'll go ahead and let you go. Thanks, everybody. I will see you in the labs on Wednesday and Thursday.